So again, in this section, we're going to do the first one at least. We're going to do both these together because the first section is really short. We're just doing another graphing example using transformations. So the last section we did the exponential functions. Now we're going to graph log functions. So an example we're going to work up to is graphing this. So maybe 2 log base 2 of x plus 1, something along these lines. And just like before, we need to start with the parent function, then we work through all the transformations. But now what we're going to need is, so what is this, the graph of log, and there's a base down here, x. So what this graph is going to look like, always is going to look like this, no matter what that number is on the very bottom. So this number right here, it's always bigger than 1, or 0, I mean. So no matter what that letter is, the number, the graph is going to look something like this. And then is this easy sort of memorize? Always this point is going to be 1, 0. So where it touches this, the x-axis, that's going to be 1, 0. And then we're always going to have this point as well, a, 1. So these 2 points are always going to be on the graph of the log function. We don't really care about finding other ones. We're always going to have 1, 0, and whatever our base is, we're going to have that, 1. And so that's basically all we need. So when we're graphing these functions, the log functions, all we really care about is, like always, just the parent function, what it looks like. So for this log function, that's what this is going to look like. And then we'll move the transformations around, like, this 2 and this plus 1. And we'll talk more in a second, like what log actually means, but for now that's not too important. We'll just know that this is the parent function, and then we'll do an example of graphing with the log. Okay, oh, sorry, let's just add one more thing to this page. So there's a special name for one log when we have a special base. So in the last class, or the last video, we talked about this function, f of x is equal to e to the x. So this e right here, we said last video, this was just that number 2.71, it repeats forever. So if we make the log of that base, so for example, log base e of x, again, so this is no different just from any number down here, it's just its own number. Just in this special case, it has its own name. We could say this is the natural log of x. So if you see log base e, it's the same thing. If you see natural log, it just means we have a log and the base is e. I guess one other thing too that might come across is that if you just see the word log and there's no base down there, that means that the base is going to be 10. So these are really the only 2 special cases. If we have an e down there, most people write that as natural log. And if we don't have anything down there, that just means the base is 10 and you just don't need to write it because it's understood that if you don't write the base, that just means the base is 10. But other than that, you need to specify. So up here, log base 2, that doesn't have a special name. We just write log base 2. Okay, let's do an example with this. So let's graph, how about we do 2 natural log of x minus 1 minus 3. Okay, so let's start with the parent function. The parent function here is just going to be natural log of x. And then the first transformation is natural log of x minus 1. The second transformation is this 2 natural log of x minus 1. And the third transformation is going to be, we have the 2, the natural log x minus 1, and then minus 3. Okay, so let's start just by graphing all of these separately. Let's start with the natural log of x. So just off to the side, remember when we write natural log, like we said on the previous page, this is just another way of saying log base e of x. All right, so let's start with the parent function. We said no matter what, the graph of a log with any base looks something like this. And which I guess what I didn't mention is that this line gets really close now to the y-axis. It doesn't cross it ever, but it's going to get really close to it. And each log always has the same points. This point right here is always going to be 1, 0. And then this point over here is the base, 1. So here our situation, our base is e. So this is going to be the point e, 1. Okay, so that's good. Here's natural log of x. So now let's move on to the natural log of x minus 1. Well, remember, so this minus 1 is directly to the x, so it means we're going to move everything over to the right 1 unit. So let's draw another graph. But now this is, so remember, we'll start with the points. We're moving all these points over 1 unit, so move this over to the right, now it's going to be at 2, 0. Move this one to the right, 1 unit, now it's going to be at e plus 1, comma 1. So that gets moved over to the right. But now, so look what we're doing here. We're getting really, really close to this line, the y-axis. So the y-axis, another way of saying that is that's just x equals 0. So remember, x is left and right. So on this line right here, we don't move left or right at all. It's just x equals 0. But we're moving everything to the right 1 unit, so we're adding to all the x's. So if we're really getting close to this line here, we move everything to the right, now we're going to get really close to this line at x equals 1. So now our graph looks like this. Okay, so same shape, just everything moved over to the right. So here is natural log of x minus 1. Okay, let's move on to the next one, which is 2 natural log of x minus 1. Okay, now this 2 is on the outside, meaning we multiply all of our y values by that 2. So this has a y value of 0, multiply it by 2, it still stays 0. So 2 comma 0. This has a y value of 1, multiply it by 2, it's going to be, so e plus 1 comma 2 now. Now let's think about this one. All of our y values on here, well, they're clearly different, so they move up and down. But the main thing is that this line always has an x value of 1. If we multiply all of these y values on this line by 2, that doesn't change the x values. So we're still going to have every one of these points on here are still going to have x values of 1. So really multiplying everything on this line by 2 doesn't going to change anything because the x values are still going to be 1, so it's still going to be this line x equals 1. So when we multiply by a number here, this line's not going to move to the left or to the right at all. So we're still going to get really close to that line at 1. So again, let's think about that. We have this line right here. This is the line x equals 1. And it doesn't matter, so like, here's a point on here. We can call this point, about 1 comma 10. If we were going to multiply that y value by a 2, so now it's going to be at that point 1 comma 20. But the main thing is that that point didn't move to the left or to the right. All it did, that point was moved it up a little bit. So now it's up here. But so that's going to happen with all of these points. All of these points are just going to move up a little bit. They're not going to move to the left or to the right. So this line is not going to move over. And this is the line we're getting close to. So all this, nothing really changes when we multiply all these y values by 2. The x values stay the same, so we're still going to get close to that line. Okay, now the last one is minus 3. Okay, so minus 3 is on the outside of the x, so we're going to take all of our y values and subtract 3 from them. Here's a y value of 0, that's going to move down here now, 2 minus 3. Here's a y value of 2, but now that's going to be right here, e plus 1 minus 1. Okay, now again, let's think about what happens to this line if we just subtract all the y values by 3. Again, we're only messing with the y values here, so these x values are not going to change. So, for example, this point is just going to move down. Here's the point 1, here's that line. This point's just going to move down, now it's going to be at 117. But the main thing is that this line's not going to move to the left or to the right. It's only going to be moving up and down. So we're still going to get close to this line. So we still get close to that same line. So we move up over here. Okay, and so then this will be our final answer. This is the graph that we're looking for. Okay, so that's everything. Basically the only example that we need from section 4.4, or sorry, 4.3. So this is all going to be the 4.4 stuff. So the first thing I'm going to talk about is just a couple of rules with the log. So these are all very important. This is like basically all we're going to be using in this section. So the log of any base, and we put two things on the inside, say an x and a y. This is the same thing as log base a of x plus log base a of y. So now the second one, if we do x divided by y, this is going to be log base a of x minus log base a of y. Okay, now the third one. So if we have a exponent on the inside like this, we can take this exponent, move it to the front, and then multiply it by log base a of x. And then the fourth rule that we'll have is if we have log base a of a, this is going to be 1. And then log base a of 1, that's going to be 0. So these 5 rules are going to be important in this section. And let's sort of just talk about, like, so what does the log mean? So in the previous section, we had this equation, just f of x. Well, let's use y's actually. So we have y is equal to a to the x. So what this means, this is another way of writing the log base a of y is equal to x. So these two equations are related. So say if we have y is equal to a to the x, that just means the same thing as this. Log base a of y is equal to x. So in a way we can think of them as sort of like inverses of each other. I guess it's not too much more important beyond that. What's mainly important from this section is just knowing these properties. So let's do a couple of quick examples. So let's say we have, we want to simplify something like, let's do log base 2 of 8. So say if we want to simplify something like this and we want to use some of these properties over here. So the goal when we always are simplifying things like this, so a log with a base, and then there's just a number on the inside, so in this situation 8, we want to figure out a way, how can we rewrite 8 as whatever this number is, so this 2, raised to some number. And the reason why we want to do this will be clear in a second. So just if we started thinking for a second, so let's plug in 1 here. That's 2 to the 1, which is 2, that doesn't equal 8. Let's try the next one. 2 to the 2, that's 4, that doesn't equal 8. But if we did 2 to the 3, that's 2 times 2 times 2, that does equal 8. So we can see that 8 is 2 to the 3rd power. All right, so now what we want to do is just replace this 8 with 2 to the 3. So log base 2 of 2 to the 3. Again, nothing changed here. Instead of writing 8, we're just writing 2 to the 3rd power. Now the reason why we want to do that is, so normally we would need a calculator to simplify these things, but there's specific times where we don't. And this is a time that we don't need a calculator. So because we can write 8 as 2 to the 3rd power, so what we're going to use is now this property number 3 that says when we have a power on the inside, we can bring that power to the front and then just rewrite the log that has the inside without the power. So we're going to put this power 3 into the front, so it's going to be 3 times log base 2. And we get rid of this power, so now we just have a 2 on the inside. But now we look at this property. Whenever this base and the inside are the same number, it just equals 1. And that's what we have right here. The base is 2 and the inside is 2. So this is going to equal 3 times 1, because whenever the base and the inside match, we have 1. And 3 times 1 is just 3. So we're able to simplify this one without a calculator. We can simplify log base 2 of 8 is equal to 3. Let's do another example like that. How about, say if we wanted to simplify log base 3 of 1 over 27. Okay, now the goal last time, like we said, was can we rewrite this inside 1 over 27 as that base to some number? That's what we did here. We wanted to rewrite 8 as this base raised to a number, and we saw that that was 2 to the 3. So let's see if we can do the same thing for 1 over 27. Can we write 1 over 27? Can this be equaled as 3 raised to some power? Well, let's think about it for a second. If we did 3 to the 1, that's 3. That doesn't work. If we did 3 to the 2, that's 9. So that's not the same thing. But if we did 3 to the 3, that's 27. But we want 1 over 27. So what we can see is that 1 over 27 is actually equal to 3 to the minus 3. So again, why is that? Well, let's simplify this a little bit down here. So if we have 3 to the minus 3, remember a minus exponent just brings something from the top into the bottom. So this is going to be 1 over 3 to the 3. And 3 to the 3 is 27, so 1 over 27. So we can rewrite this 1 over 27 as 3 to the minus 3. So let's do that. We'll have log base 3 of 3 to the minus 3. And just like before, this power, it can move into the front. So we're going to have a minus 3 times log base 3 of 3. And then again, like before, we have this inside, the base and this thing match. So that just equals 1. So this is going to be minus 3 times 1, which is equal to minus 3. Okay, so there's two quick little examples from just simplifying what logs are. All right, now let's do A couple more examples. So this next is going to be called expanding. So what we're going to want to do is, so for example, all these examples are going to be for expanding. So what we're going to do is we want to expand, say, log base 3 of, how about ABC? So let's think about this for a second. Let's write some of those rules back over here again. We had this one rule that no matter what the base was, if we have things multiplying on the inside, this is just going to be log x, log y. So whenever we have two things multiplying, we can break it up with multiplication. So how about, let's think about this as just this a and this b are multiplied together. So we have a times b, so that's one little piece, times c. So that's okay, that's still the same thing. We can multiply in any order we want. So let's think of this as one piece, AB, and then multiplied by C. So we can use this rule over here to expand this out. We have AB times C, so we can write this as log base 3 of AB plus log base 3 of C. So all we're doing is using this property here. We have this piece times this piece, this piece times that piece, so we can break it up with addition. But now when we get to this step, we see we have that same thing again. Here we have a plus b. So this is going to be log 3a plus log 3b plus log 3c. So what this is, and now we're done here. There's nothing else we can do. This is an example of expanding. So we took one log and we broke it up and we wrote it into many different logs, all added up like this. So let's do another example. Maybe one's a little bit more confusing. So let's say if we have log base 2 of x squared over z times y. Okay, now let's write one more log rule, or let's write two more log rules over here. So you remember we have this one. If we have division, this is just log base a of x minus log base a of y. And then we've used this one before in the previous example. If we have a power, we can bring the power into the front. Okay, now for this problem, let's start by using this property, this middle one right here. We have division, so we have this piece, the x squared, divided by this bottom piece. So we know that's going to equal the top piece minus the bottom piece, zy. So here's our top piece. Whenever we have the top and the bottom, we do the top minus the bottom. So we're doing the top minus the bottom. And each of these, we need these parentheses here. These are important to the problem. It keeps everything nice and organized because these are both individual logs. We have the log of the top minus the log of this bottom piece. Okay, so now for this first piece, let's look at this property. If we have a power, we can bring it into the front. Here we have a power of 2. We're going to bring it into the front. Okay. Nothing else we can do now, so no minus sign. Now this piece, we have multiplication. But remember, multiplication means we can break it up with addition. So this is going to turn into log base 2 of z plus log base 2 of y. And the reason why I'm putting this in parentheses is because this minus sign belongs to this entire thing. So when we rewrite this piece as log base 2 of z, log base 2 of y, that minus sign belongs to all of it. So we need to distribute the minus sign. And then doing so will give us our final answer. So we'll have log base 2 of x minus log base 2 of z minus log base 2 of y.